Bismillahirrahmanirrahim. Assalamu alaikum dear students. I am Arif and I welcome you all to lecture number 40 on the subject of computer organization and assembly language programming. The title of today's session is Control Instructions Part 2. Well, today's session is a continuation of the previous session in which we discussed as how the flow of execution of an assembly program can be changed using the unconditional JMP instruction and different signed and unsigned conditional JCC instructions, where CC is the condition code for the jump. In the last session, we learned to design the if-else control structures using the conditional jump instructions, and today we will learn the design of repetition structure like the do while and the while using the conditional jumps. Later we will see the x86 loop instruction that is specifically designed for the looping purpose. So let us first have a quick recap. Well, this slide shows the register set of x86-64 microprocessor that we discussed in detail in lecture number 28 of this course. This slide summarizes the x86 programming tool chain and the layout of assembly program that we discussed in length in lecture number 29 and 30 of this course. And this slide shows the different categories of x86 assembly instructions that we intend covering in this course. And today is the second session on the control transfer instructions. Well, dear students, in the last session we talked about the unconditional jump instruction, JMP, which is a single operand instruction and unconditionally transfer the flow of control of execution to the destination, which can be an immediate value, register, or memory contents. Well, using this jump instruction, a programmer can perform a short, near, or far jump and a task switch as well. In this example assembly program that we discussed in the last session, due to this jump instruction shown in red, the control of execution will transfer to this label underscore end over here, and these 5 lines of code will never get executed. Well, dear students, unlike the single unconditional jump instruction, x86 offers many different conditional jump instructions whose mnemonic start with the alphabet J followed by one or more characters representing the condition code. Well, a conditional jump is mostly followed by a compare instruction which sets or resets different status flags, and based on the value of those flags, the jump is either performed or not. Well, these tables summarizes some of the signed as well as the unsigned conditional jump instructions that we used in the previous session to write down assembly programs corresponding to different high-level if-else code snippets. And in today's session, we are going to write down assembly programs that will correspond to different repetition structures that we normally come across in high-level languages. So let us start with a do-while loop. Well, this is a code snippet that represents a do-while loop in C syntax. Note the instructions inside the loop body will execute at least once, even if the condition is false. And this is because the loop condition is checked or evaluated at the end of the loop. This is one possible way of implementing the high-level code using assembly language. Note the RAX register. This represents the loop counter, that is I, initialized with 0. This label represents the start of the loop body. The loop instructions comes over here, and for simplicity I have not kept any instructions over here for the time being. This increment instruction corresponds to this I++ instruction over here. Finally, these two instructions check for the loop condition. Since RAX contains 1 right now, which is of course less than 5, so this conditional jump instruction JL saying jump to this label underscore loop body if the first operand of above compare instruction, that is 1, is less than the second operand, that is 5. So this will evaluate to true. Therefore the control will be transferred to the first instruction after the label loop body, that is over here. And this will continue until RAX becomes 5. When this conditional jump, that is if first operand, that is RAX, is less than second operand, that is 5, will evaluate to false. And this jump will not be performed. And the control will move on to the next instruction in sequence, which is the code to gracefully exit the program. Okay, so let us now move on to the Linux terminal and execute this program inside our favorite debugger, GDB. Let me show you the code first, do while.nesum. This is the same code that we have discussed on the slide. Let me assemble it using nesum -f-elf64, the file format, -g for adding the debugging symbols. Do while.nesum will generate the .o file. Let us link do while.o, and let's load this executable, that is a.out, inside the debugger using the text user interface mode. Great. Let me put a focus on the command window, put a break at the label underscore start. Let's see the registers as well by setting the layout to reds, and let's run the program. Okay, so right now the control is at instruction 11, move RAX, 0. Let me press SI to execute this instruction. We have moved inside the loop body. This instruction will increment RAX. You will soon find a 1 over here. This compare instruction has compared, and since 0 is less than 5, which is true, so this instruction will transfer the flow of control to the first instruction after this label underscore loop body. Let me press SI again. Note the RAX register as I keep continuing. It is incrementing 3, 4 and 5. Now the RAX contains 5, and once we execute this conditional jump instruction, it will evaluate to false because 5 is not less than 5. So now the control will not move to the loop body, rather will exit the loop body and move inside this code, which is used to gracefully exit the program. Let me press C to continue. Let me press Q to quit, and let us fall back to the slides again. Okay, so far so good. Well, after the do while loop, let us now talk about the while loop construct. Well, in a while loop, the condition is checked at the start of the loop. And if the condition evaluates to false, the loop body will not execute at all, and the control will come out of the loop body. This is the main difference between the do while and the while loop. And this is the C syntax of for loop construct, which also checks the loop condition at the start of the loop. And this is one possible way of implementing the while and the for loop construct in x86 assembly language. Note that first of all, we need to initialize the loop counter as we have done in the do while loop, that is initializing RAX with 0. You can use any other register in place of RAX. Well, the difference comes over here when we check or evaluate the loop condition before the loop body. In the C code snippet, the condition to evaluate the loop body is I is less than 5. And over here we have used the reverse condition. Jump if RAX is greater than or equal to 5 to this label end of loop, that is over here, out of the loop body. Anyways, right now, since the condition is false, so the jump will not be performed and the control will move on to the next instruction in sequence, which is the loop body. This label represents the start of the loop body. The loop instructions comes over here. For simplicity, once again I have kept no instructions inside the loop body. Once the loop instructions executes, this increment instruction increments the loop counter. Well, dear students, you can use decrement instruction as well, in which case you will initialize RAX with 5 instead of 0. Anyways, finally these two instructions checks for loop condition again. If the contents of RAX register are less than 5, the control will be transferred to the first instruction after the label underscore loop body, that is over here, to repeat the loop instructions. Otherwise, the control will move to the next instruction in sequence, that is code to exit the program will be executed. My dear students, one more point that you might have observed is that in the assembly code, the loop condition is checked at two different places. And at these two different places, we have two different conditions. Over here, we have used jump if greater than or equal to move to the end of the loop label. And over here, jump if less than. Well, dear students, download this assembly program from the course Bitbucket repository, assemble and link it, then load and execute it step by step inside the GDB to have a clear understanding of the working of the while loop construct. And I move ahead. Well, to implement the repetition structure, x86 also provides an instruction called the loop instruction. And for completeness, let us study this as well. Well, this slide shows a brief description of the x86 loop instruction as well as a sample assembly program that makes use of it. Well, this loop instruction performs a loop operation using the RCX register as the loop counter. and is used to perform a short jump only uh, to this label, which is its only operand. The loop instruction, as shown in red over here, when executes, automatically decrements the contents of RCX register, that is the loop counter, and jump to the label underscore loop body until the contents of RCX register is not equal to 0. So when using a loop instruction, a programmer initializes this RCX register with the number of times he or she wants to execute the loop body, and at the end of the loop body, just write down this loop instruction. No need to explicitly decrement the contents of the loop counter, as we have done in the case of the conditional jump instruction in our previous example. Well, there are other variants of loop instructions like loop E and loop NE, which additionally check for the 0 flag as well when making the decision to jump. Okay, let us now move on to the Linux terminal once again to have a demonstration of this code snippet. Let's clear the screen. Let me show you the program loop.nesum. This is the same program that we have discussed on the slides. Let me assemble it. nesum-felf64-g loop.nesum. Let us link loop.o and let us load this executable inside GDB in quiet mode in text user interface. Let me put a focus on the command window. Let me put a break at the label underscore start. Let me show you the registers as well by setting the layout reds, and let us run the program. Great. So this is the first instruction, that is initializing RCX with 5. Right now RCX contains 0. Let me use SI to step into. So note that RCX now contains 5. The loop instructions have been executed. We are at the instruction loop, which will decrement the contents of RCX by 1 and will move to this label loop body until RCX becomes 0. So let me press SI again. Note the contents of RCX are decrementing. Let me press SI again and again and again and again. So when RCX becomes 0, this loop exits and the next instruction after the loop, which is the exit system call, starts executing. Let me press C to continue and let me press Q to quit the debugger. Well, dear students, to have a better understanding, let me show you another program that do something constructive inside the loop body, that is vimfinal.nesum. Well, this program prints a string PUCIT on std out 5 times. Inside the data section, you can see the variable msg containing the string PUCIT along with a new line character having a length of 6, and this is the length of this string. And inside the loop body over here, you can see these are the 5 additional instructions that use the write system call to display the string on std out. And since RCX is initialized to 5 decimal, so this loop will execute 5 times. until RCX becomes 0. So this string PUCIT will be printed on the standard output 5 times. Great. Let me assemble this program. nesum-felf64-g final.nesum, let us link final.o, and let me execute it straight away. Oops. It appears as if it has entered in an infinite loop. Let me press Ctrl C to exit the loop, terminate the program, and let us load this program in GDB and see what is the problem. GDB -q a.out-tui, put a focus on the command window, layout reds, break at the label start. Let's run the program. Excuse me. Okay, fine. So here we are. Note the RCX register is being initialized with 5 in this instruction. Let me press SI to execute it, and RCX contains 5. Now these are the loop instructions which are setting the system call number inside the RAX register and the 3 arguments inside RDI, RSI and RDX. And finally over here we are calling the syscall. Note the contents of RCX is 5. Also note the contents of RAX is 1. Let me execute the syscall by pressing SI again. And now you see the syscall after its execution has changed the contents of both these two registers. RCX has been set to some unknown value and RAX contains 6. Well, as far as RAX is concerned, we know that once a system call executes, it places its return value inside the RAX register. And since this is a write system call, so it has placed the number of bytes that it has written on the screen inside the RAX register. And of course the string PUCIT along with the new line character counts to 6, and that is why RAX contains 6. But I don't know why this RCX contains this value. However, different library calls as well as system calls make use of different registers, and since the code of the write system call is not right in front of us, so it might have used RCX register as well. So that is why the RCX register has changed. Let me step into again. So it is again executing, and again we are on syscall, and after that again you see the same value 401020. Let me do it again, and after the syscall executes you see again the same value over here. So we have identified the problem. So we need to modify our program a little bit to make it work. So let me press Q to quit and open this program inside editor. Let's suppose Vim. So the problem is over here. Whenever this syscall is made, the contents of RCX are changed. We need to save the contents of RCX register. We need to preserve it because it is a loop counter. So we need to save the contents of RCX register before making the system call, and set RCX to the old contents after the system call has been made. One way of doing this is pushing the contents of RCX on the stack. Let me do that. So over here, let me push the contents of RCX register inside the stack, and over here let me pop it back to RCX after the system call is made. Fine, I think it should work. Let us save the program and exit the editor, assemble it again, -f elf64 -g final.nesum. Let us link ld final.o and let us load again inside GDB in quiet mode a.out -tui. Let's put our focus on the command window, layout reds, break to label start, and let me run. Great. So once again we are over here, move RCX, 5. Just remember, we just have used these two new instructions, one before the syscall and one after the syscall. Let me press SI and execute this program. We have entered inside the loop body. Fine. Moving ahead. And over here, before making the system call, I am pushing the contents of RCX on the stack. And the contents of RCX are 5. Right now I am on the syscall. Let me show you the contents of the stack by using the examine command, xg $rsp stack pointer. So the top of the stack contains 5. That is great. Let me press SI to execute this system call, and you can note that after this system call will execute, the contents of RCX will not be 5, rather something else. Yes, it contains the same old value 401021. After this pop instruction, the contents that we have saved on the top of the stack will be popped and placed inside RCX. So let me execute this pop instruction by writing SI again, and there you go. And now we have the loop instruction, which will of course decrement the contents of RCX to 4, and since it is not 0 yet, the same code will be executed again. Let me keep pressing SI. You see the system call has come, and we have again fall back to the loop body. Let me press C to continue. So we have PUCIT once, twice, thrice, 4 times, and probably it has printed one more time before as well. Let us quit the debugger and let's simply run this program on the terminal and see that is great. So string PUCIT has been printed 5 times. Well, let us fall back to the slides. We have done our job. And well, this is the code that caused the infinite loop because this write system call is changing the contents of RCX register, and thus again and again the same loop keeps on running. And over here we have handled the problem, and this is how we have pushed the contents of RCX register on the stack, and here we have popped that. So this has solved the problem. And remember, you need to preserve the value of the loop counter inside the body of the loop. Apparently it appears that RCX register is not being changed by our code. However, the system call code is changing the contents of RCX register. So make it your habit, whenever you are making a system call, library call, or maybe a assembly procedure call, you need to save all those registers which you are expecting to be affected by that system or library call. Okay, so that is all for today's session, my dear students. I hope it was informative for you all. If you have liked it, please subscribe my YouTube channel and share it with your friends. I wish you all the best, happy learning, and Allah Hafiz.